for next time.
Okay, welcome everyone. Second lecture, Best for Data Science. Today we'll be talking about perception. But first, are there any administrative questions? As you might have seen, homework 1 has been released. Homework 1 is a very simple warm-up exercise. I'll be teaching about SVG, what you need to know, next Tuesday. The first two homeworks, we'll try to always release them on Wednesday or Thursday. The first two homeworks, you will only learn the stuff that you need for the homeworks on the Tuesday before. And they're like a lot shorter because of that, and so you should still be able to easily manage that, or you can also study ahead a bit. Okay, so let's talk about perception. What is perception? Understanding, that's part of it, but like what do I mean by perception? Point of view? Point of view? Yeah, so I'm talking mostly about visual perception today. So we'll be talking about things like how does the human perception work? What is the difference between perception and cognition? How does color work? What are kind of like some psychological effects that we know that we have to be aware of when we want to design visualization? So like this is like this high-level distinction between perception and cognition. Perception is the identification and interpretation of sensory information, and that's really about from the physical stimulus, like in the case of light, to recognizing information. And perception is, of course, shaped by our experiences, by learning, by memory, by our expectations. Cognition is like a higher level process where it is really all about processing of the information and applying knowledge. And kind of like the example that I think makes it useful that makes the distinction clear is to hear somebody speak, also in a foreign language. That's perception, but understand the language and the words, that's cognition. So that's the difference here. So the perception is associated with things like the eye, optical nerve, the visual cortex, basic perception, the first basic processing that our brain does, like edges and planes. It's usually not conscious, and it's also what reflexes use. So for example, if I were to come close to you and were to punch you from the side, you would recognize this as a perception process and evade my punch. Cognition is about recognizing objects, making sense of relationships between objects, about drawing conclusions, about problem solving, and about learning. So here is kind of the difference between perception and cognition, right? So we have like these words that represent colors are shown in different colors. So the initial stimulus, the perception is blue for this brown one here, but then when we think about it, it's of course the cognitive part is brown. So one important distinction is that what we see is not necessarily what is really in the world. And we use these effects, and the same projector is flickering in. So what we see is not necessarily... Okay. What we see is not necessarily what is in reality. So for example, if we look at the 3D scene on a computer, like it's actually not a 3D scene, right? It's just like created to look like a 3D scene. And there's some examples for that. So who can spot something interesting on this picture? Like raise your hands if you see something. Okay, so there's a Dalmatian here. This is the head, you see like the ear, and then here is the shoulder, the leg, and the body, and then the leg. Is this, like, do you think you could train a computer vision algorithm to see that? That might be really hard, right? That's some like really, like that's what we call like Gestalt principles, and we'll be talking more about that later. This is like, these are called emergence images. And once you've seen this dog, you will not be able to unsee it. So next time I'll share this picture, years from now, you will immediately recognize this dog. and that's called perceptual hysteresis. And there is some other pictures here. So who can, like, raise your hands when you can recognize something? Okay. What do you see? An elephant, exactly. And so there's a paper that published creating those, like automatically creating those images. It was a SIGGRAPH paper. And also, like, if you only look at patches, then it actually doesn't work. So this, like, if you only looked at these patches here on the left in isolation, you would not be able to recognize the elephant. So you need the whole thing to actually be able to recognize this. This is, like, again, a classic example of something is being drawn to work, like, in your mind as a three-dimensional scene, but of course in reality, this is how that looks like. So we do rely a lot on priors, right? We kind of, like, whenever we look at something, we try to match it with something that we are familiar with. And so if there is, like, something that looks like a foot, we might actually interpret it as a foot. And there's, like, these figures that are kind of like where our priors kind of, like, don't work properly for us. So if you think about those images, you can see what is going on. But of course, they look really odd when you first glance at them. Pareidolia is the effect of like seeing faces in things where there are no faces. So here we have, like, the magpie, the cute magpie, a face like a sad pickle, a thinking friar, and then those, like, exasperated chairs here. And that's because we kind of, like, tend to look for faces. Like, faces are very important in our, like, development, and so we really look for expression for faces and so on, and therefore we tend to spot faces even when there are no such faces. And you have probably heard of, like, the picture of Jesus Christ on the toast. That's like an example of that. So the take-home point here is that vision and our perception of it is constructed top-down from the input. And this quote is quite useful. What you see when you see a thing depends on what the thing is. What you see the thing as depends on what you know about what you are seeing. So let's take a step back and talk about some low-level, like, biological processes. And this is not going to be, like, a deep lecture on biology. I just want to give you an idea of why it is that we see things differently. So, like, you see it in high school biology, probably, like, schema like this. Of the eye, you have things like the pupil, the lens, the iris, the fovea, optical nerve, and the retina as kind of the main components of the eye. And all of these have important roles. Essentially, the lens is used to focus the light, and on the retina, we actually have the sensors, the rods and cones, that are responsible for our perception. And then at the point where the optical nerve exits the eye, we don't have any rods and cones, and that's where we have our blind spot. The human visual system, there's about 5 to 6 million cones, and the cones are responsible for color vision. These are really densely aggregated at the center, at the fovea. So we see color really only in a very, or not only, but mostly in a very narrow area. And you can remember cones because it's like color, first two letters. In contrast to that, we have the rods, where we have many, many more. We have 120 million rods, and they're responsible for black-white vision, and also, of course, for low intensity, like scenarios when it's almost dark. And the fovea is responsible for sharp central vision, and the fovea has only cone cells. And so this figure here is quite telling. This is the concentration of cones along, like, degrees from the fovea. And so you can see that they're really concentrated around the fovea. So rods are sensitive to black and whites. Cones are responsible for color vision, and then in the back end here we have the ganglion cells. These are microscopy images of these rods and cones. And here's a picture of the fovea, and you can see, like, these are the cones that are responsible for different wavelength. And so you can see that we have more cones that are responsible for red and green wavelength than there are for blue wavelength. And so we also have a harder time usually seeing shades of blue than we have for red and green. This is like a similar diagram as we saw before. Here is like the distribution of degree photophobia of cones and of rods. And so you can see this kind of like alternating pattern that where we have a lot of cones, we don't have many rods, and then there's nothing in the blind spot. And here are the wavelengths that we perceive, where we have these, where our cones can actually perceive the color, and that's blue, green, and red at these different wavelengths. So you might actually think that your eye works like a digital photo camera, where like everything is perceived at the same time. Like the pixel on the bottom right is perceived the same way as it is in the center, but that's actually not how it works in fact. So like if you were to look at a spreadsheet, what it actually looks like is this. And you only get the perception of this being a continuously sharp image because you move your eyes. So it's not actually that you see everything sharp all the time. And so the human vision works as a series of fixations. This is when we actually perceive something, and saccades, when we move our eyes between the points where we have our fixations. So fixations, we maintain the gaze on a single location, which usually takes between 200 and 600 milliseconds. And in the saccades, we move between different locations in 20 to 100 milliseconds. And so vision is not similar to a camera, it's more similar to a dynamic and ongoing construction project. As you like explore a scene, you understand more about it, you memorize information where it has been before, and therefore you perceive it as like an ongoing scene. Here on the right, this image shows you like the different colors are different paths of how people, when they looked at an ad like this, how people looked at this. And so you can see that like these are called gaze plots, and so they show like the dots here show the fixations, and so you can see that obviously people are looking at the person's face and the eyes first. This is a video of like an aggregated, for many people, where they look in a video. So these things are used to study, for example, ads in marketing, or they're also used in mobile environment to study like where do people look when they walk through a supermarket aisle. But we also use those eye tracking instruments in research to understand where people look when we present them, for example, with a visualization. So I've done eye tracking studies myself to understand how a particular visual encoding works. This is how an eye tracking setup looks like. This is like a pretty intense one, the kind of thing that you would use for a perceptual study, because you're actually your head rests on a chin rest, so you're not moving. There's now much less invasive ones, like as you can see here on the right or on the left, where there is some computer vision happening that they track your head and so on and correct for that automatically, that you can interact with this more naturally. And so what we have here is an infrared camera that records your eye. And then we have a display where we have our stimulus, in this case a visualization. And then this is like what the camera sees. So it sees your eye, and then it tracks where you look at. And so this is a video of taken with a software and a tool by one of those SMI, sensomotoric instruments, is a vendor for these eye tracking systems. This is just a demo video so that you get a sense of what this looks like as an analyst. Oops. So what you see here, other than the beautiful singing that you hear, is how we read. So we don't actually have like a continuous gaze, but we have this a sequence of fixations and saccades that basically stop on words or on like word moves for us to perceive the text. And so the human visual system is like we don't actually have general purpose vision. What we see really depends on our goals and expectations. So we are really good with relative judgments. So for example, if I showed you two color tiles, they were slightly different, I would place them next to each other, then you would be able to recognize slight differences. If I placed one over here and one over there, you would not be able to see those differences. We're not so great at absolute judgments. And then of course we are easily fooled by our preconceived notions of what a scene looks like. So what do you think is going on here in this picture? Is this really a giant, a regular person, and a dwarf? No. Exactly. So this is a setup where you have a non-rectangular shaped room. And so here is a video of this. And obviously this room is carefully constructed, and you'll see soon when the camera moves how it actually looks like. But even if you know it, it's really hard to shake the perception of this being a regular room. Okay, so color is an immensely complex topic. It's immensely complex from the physics. It's immensely complex from the human perception aspect. There's quite a lot of things that you have to be mindful of if you design with color. And so we'll be talking about color today from a perception point of view. This is not going to be exhaustive. There is lectures like there are just about colors. But I'll try to give you some introduction. We'll be talking more about color for encoding data when we talk about the marks and channels for visualization. So what is color? Color is the visible part of the electromagnetic spectrum. So electromagnetic waves at the length of 390 to 750 nanometers. And so we distinguish between spectral colors. These are the colors that are evoked by a single wavelength. You also call those monochromatic colors or rainbow colors. And these are the ones like that you're all familiar with: red, orange, yellow, green, blue, and violet. Of course, these color classifications, they are more or less arbitrary, and there is of course like a continuity between them, but it's still useful to have those terms for the colors. Other colors that are not spectral colors are unsaturated colors, and those are a mix of multiple wavelengths. So for example, purple, magenta, and everything that we perceive as white or gray light is a mix of multiple wavelengths. And color is also not exactly equal to wavelength, but rather color is a combination of wavelength and energy, so the intensity of the stimulus. So for example, the same wavelength, if we have a higher intensity stimulus, we would perceive it as yellow. If we had a lower intensity stimulus, we would perceive it as brown. So if you really want to talk about the physics of color, you need to also specify wavelength and not just intensity and not just hue if you talk about light. Color vision is in fact actually irrelevant to much of normal vision. So you could be a completely perfectly functioning human being without color vision. Especially in nature, you will be fine, because most of the things that we really rely on is all about just contrast and seeing shapes and so on. So it doesn't help us to perceive the layout of objects. It doesn't help us to perceive how things are moving, what shape they are. What color does, and this is kind of like the hypothesis of why color developed evolutionarily, is because color breaks camouflage. So it's easy to spot, for example, the red cherries here in the leaf of in this many green leaves. And it also tells us about the material properties. So for example, by using color, we are usually able to judge the quality of food. So is an apple fresh or is it rotten? And it changes color for that. And so these are theories of why color vision developed. The dimensions of color, when I say color, I usually mean color hue. And color hue is essentially the wavelength, or like the combination of wavelengths. In contrast to that, we have saturation, which is the purity of a color, and value, which is also called luminance and brightness, which is the lightness or the darkness of a color. High saturation colors have usually medium values. And so we'll talk about how to use these three different channels to encode data at a later point. So what is the role, like why do we perceive objects with a certain color? Because this is all about refraction. Like if we have an object like the carpet here, which is red, what actually happens is like white light hits the carpet and only the red light is being reflected from it, and that's why we perceive it as red and everything else is absorbed. And so here are some examples of how that works for orange, green and red objects. I also want to recommend that you listen to this Radiolab episode, which is called Ribbon, the Rainbow, a New One, and the follow-up to it, Ribbon, the Rainbow, an Even Newer One. And that they really discuss, and this is really well done, they discuss how like color perception works, what are the distinctions, this different color perception, like what we think about how color perception works in various animals. So for example, the mantis shrimp can perceive many more colors than we are, but then other researchers found out that they can perceive it, but they cannot distinguish it. So anyways, basically this episode is about the perception of color and about how different kind of like animals perceive color. So it's really nice. I would play it, but it's a rather long thing here. So, question. What are the primary colors? 1, red, green, blue. 2, red, yellow, blue. 3, orange, green, violet. 4, cyan, magenta, yellow. So who thinks it's 1? Who thinks it's 2? Who thinks it's 3? Who thinks it's 4? Graphic designer? For print. So the thing is, all of the above. Primary colors are really depend on your context. So what do I mean? So for example, when I do paint mixing, I actually physically use cyan, magenta, and yellow, the secondary RGB. And then this is also a subtractive model. You have probably heard of CMYK. That's another color model where you can also separately represent true black. And then light mixing, this is what is happening on this projector or on your LCD screens in your computer, is the additive mixing of colored lights. And so here we have the classical RGB and the secondary CMY, and this is additive color mixing. And so when we talk about digital color or light-based color, this is what we usually refer to. And so the thing is that basically this is a chromaticity diagram. And so how this chromaticity diagram works is that along the curve of that diagram here, you have all the spectral colors. And then in here you have the colors that are a mix of these different wavelengths. And so if you, for example, were to pick 3 points in here, or 2 points, let's say, if I have pixels of that color and then pixels of that color, I could represent all of the colors along that line with a device that only has those 2 pixels. And if I have 3 colored pixels, like here, then I can present all of the colors in that triangle here. And so this is how computer screens work, and that's also how why there are some colors that we cannot actually display on a computer screen. So because there's some colors that are outside of the gamut. So what you can see in this diagram is that the least saturated colors are at the center. I think that basically I've explained everything else about this diagram. So I basically said this before, but Here the point that I always wanted to make is like this is like what a typical display could display, and here you see different color models. So Adobe RGB 98 has a bigger color gamut than like standard RGB, and then CMYK has like a non-linear color gamut and hexachrome and so on. So you see that you can create those gamuts with multiple colors, but in many cases 3 colors are a sufficiently good approximation. And then that's why the primaries here are more or less arbitrary. So if we talk about color for visualization, we want to talk, of course, about color maps. And we'll be talking more about this. So a color map specifies a mapping between color and values. So we have, and we need to distinguish between a couple of different classes of data, and we'll be talking more about this. For example, categorical color versus ordered categorical, sequential versus diverging, segmented versus continuous, univariate versus bivariate net. And so what we call expressiveness is matching a color map to the attribute characteristics. And so here, for example, if I have a linear interval between 0 and 8, this would be an appropriate color map for that. But if I had, let's say, unordered colors, that could, like categorical unordered colors, that could be a useful color map. If I had sequential, this would be one. This would be a diverging color map, where I have like a focal point or like a central point in my data that is meaningful. And only univariate versus bivariate. And here is like a continuous color scale. And so we'll talk more about this stuff when we talk about encoding. But basically what we can use color for is labeling. So here is a carefully designed color scheme for 12 colors. As we'll see later, 12 colors is kind of like a lot. Usually we restrict ourselves to much fewer colors in a visualization. Here's an example where somebody tried to represent the data set with 22 different colors. So this is like, in 2 ways, an interesting map, because it's supposed to be a graph of the internet, which is kind of challenging even if it was the internet in 2002. But then they colored the different domains with 22 different colors, and they actually use, for example here, 5 different shades of green. And so obviously using 5 different shades of green in a chart like this is just not useful, right? So because I cannot really distinguish them. So what we usually say is we don't use about 6 colors. If you really need to, don't ever use more than 10 colors in practice. If you want to use color for quantitative data, you should usually use value. Saturation works, but is not as good, and you definitely should not use hue to color code continuous data. Why is that, do you think? Like, what is bigger, red or blue? Orange or green? Like, it doesn't have a natural order, right? We know that if something is brighter, that we can kind of like, and so we have one thing that is bright and then one thing that is dark, we can say this is brighter than the other one. We can't make this distinction for color. And so therefore, like, the rainbow color map or hue for the continuous color scales generally is problematic. The rainbow color map has a couple of other problems. And so here are just some examples of, like, at the top is a rainbow color map for 4 different patterns, and then here we have a continuous color map, and I think that represents best what is actually in the data, right? The continuous gradient in like the first 2 pictures, then it's like a Gaussian style continuous gradient, and then some checkerboard pattern. It kind of like looks quite different in the rainbow color map, where you have these kind of like strong boundaries, and these strong boundaries are really more of an artifact of your color scale and not really something that is natural about it. And another problem is that these boundaries on the rainbow color scale are very often not of the same size, especially if you use the proper rainbow color map, as we have in an electromagnetic light. So here are 2 other examples. This is a flow visualization with 2 different color maps. And so what you can see is like the whole flow pattern. You can perceive it much better at what is actually going on the right. The left here, where I use a rainbow color map, one thing is much easier to see though. These are the extrema, like the highest values are red. And so it's not completely clear, and Sam is kind of an expert on this, one of your TAs here. It's not completely clear why people use those color maps so much in science and engineering, but Sam has a couple of hypotheses, and I'm paraphrasing, but one of them is that it's easy to see extrema, for example, and that they're useful for binning. But you can, if you want to use a bin color map, there's better ways of doing that. Here are just some other examples of a comparison of rainbow versus color maps, and you see these kind of like artificial gradients in the rainbow color map. And these are this is an experiment for a luminance color map where the perceived grade change, this is from a human subjects experiment, and the perceived change matches, as you can see, quite well to the actual change in color. So this is like essentially the lower this line is, the better. And so we see that there's a very linear, like other than at the very beginning, where it's hard to tell apart the very dark parts, this is like a nice map. We have equal increments that correspond to the data. And the same study was done in rainbow color map, and here you can see much bigger error. So that like humans perceive the changes to be much bigger than they actually are in this color map. So this is a figure from one of Sam's papers. This is about like binning or continuous color maps. Like we usually in visualization we have the expressiveness principle that says that we should encode the data as directly as possible in the visualization. And so if you have a continuous field, like an elevation map, we should use a continuous color map. But it's not always completely true, because sometimes the binning helps us to solve certain tasks better. So here, and I guess it's a little bit hard to see on the projector, especially from later, but here is a binned colors map where we have about 8 or 10 color bins, and this is a continuous color map. And so what Sam and Blaise and some other people did is they ran a study and asked two questions. What is faster and what is more accurate? And so it turns out that for this example elevation data set, it was actually, didn't matter, continuous was slightly faster, but not really like a big effect, right? And binned was often more accurate. So people were faster in making a decision with a continuous color scale, but they were better like in terms of accuracy when they used the bin color map. So these are just some subtle considerations if you want to use color maps. Another big issue when you think about using color is color blindness, and you wouldn't actually believe how prevalent color blindness is. So if you feel comfortable, like anybody here have like a color blindness? There's 2 or 3 people here. That's about maybe a little bit less than I would expect. Like the estimates are that about 5% of all males are colorblind, and it's about much rarer in females. And I think everybody who raised a hand was also male. It's probably that the reason is probably because it's due to X chromosomal recessive inheritance. So 10% is what it says here. I've heard other figures with 5%, so don't quote me on the exact numbers. But the most common color blindness is red-green weakness. And the reason here is a lack of medium or long wavelength receptors or some altered spectral sensitivity. So that, for example, we have a green shift, that we have cone receptors that don't match exactly what other people have, but have a little bit of a different sensitivity. Here are 3 different, like the rainbow flag with normal color perception, with no green receptors or no red receptors. And you can see which kind of information you lose here. So now I'm running the test on you guys. Try for yourself. Like, what do you see here?
15, 7,
I shouldn't do that. The top? So a lot of you got it right, and these are the kind of experiments that you would run before you do, for example, a user study in visualization, to make sure that all of your subjects have proper color vision. And so it's actually like even for somebody who has perfect color vision, those are of course not easy to see, and they're designed as such. Here are just a couple of other examples of natural scenes of how something like a plant would look like for somebody who has different kinds of color diseases, like red-green deficiencies or blue-yellow deficiencies. And here's an example, like this is a visualization, we'll be talking about this a little bit more, but this was a visualization that was used in the New York Times. And red-green color blindness is quite frequent. This is how somebody who is not no red-green vision would perceive that. And they wouldn't be able to distinguish this important data point here. Like this is a green bubble, this is a red bubble. They actually look exactly the same here, right? And so that's why red-green color maps in particular are very widely discouraged nowadays. So like when heat maps, especially in biology, were becoming increasingly common in like the 2000s, they usually started out as red-green heat maps, but now people have really learned that this is problematic for a lot of users, and they're usually using red-blue color maps where these effects are much less frequent. Another example of how something looks like for normal vision or red-green color blindness, and so you kind of lose a lot of color context here. And there's also tools like this one here, the color blinder, where you can actually simulate those vision deficiencies. So you can go to this website, upload a picture, and then look for what are the different, how does my picture, and that could be like a screenshot of your visualization, how does my picture look in with various vision color deficiencies. And so here, for example, if you don't have any color vision. There's also like tools in R where you can simulate this. For example, you can throw in a ggplot figure, and then it will create these charts for you for these different color deficiencies. Another important point is that color and brightness is relative. So you've probably seen many of the illusions that I'm going to show now, but the perceived brightness of an object is relative to its background. And so what you probably all see here is that this first square here looks darker than this one here, right? And the same here, this one looks darker than this one. Now let's take a look. We have two bars here. The lower one is lighter, the upper one is a little darker, and now I'm moving them over. And you see that there is no change in color here or here. So now we actually see that the color that we perceive is actually not the color that is there in the physical stimulus. So color is relative. And the other thing that you will probably notice is that those bars which did not have a gradient suddenly seem to have a gradient, right? So I'll get them back. So no gradient. Suddenly they look like they have a gradient, and I did not add a gradient in my animation here. Which one is darker, the lower block or the upper block? The upper looks darker, and why do you think that is?
The background.
The background. It's also because of like where does the light come from in a natural environment? From the top, right? So from above. And so if something looks like this in what we are familiar with, like under sunlight, for example, we would assume that the actual properties of the above block are darker than the light than of the below block. But if I add like a square here to kind of remove the shading, you can see that they're actually exactly the same color. And this is a very, very strong effect, right? So like even if you know it, they look absolutely different. Yeah. I'm actually not completely sure about that. I think these are distractors. But you can play around this when I give you the slides later. So this is from this side here, and there's a couple of other demos. You can play with this. There is like here we have the moving dot, which seems to become lighter and darker as it moves over that gradient. But if we add like a constant, colored rectangle, we see that it actually stays exactly the same. There's many other illusions in here, and you can just play with them if you're interested. Here's the corn sweet effect that I mentioned earlier. Of course I had to have this in here. So the dress, is it black and blue and white or gold? So it doesn't really matter what it really is, right? But what matters is that it really depends on the light. And so here, this is kind of like a nice illustration of this. If you take this snippet, like cut it out, and move it under these like transparent, translucent colored layers that kind of simulate light, you can see this effect by yourself. So it's really about what color is your light to kind of judge these kinds of effects. Here's another example. Which one, where does the X look darker, on the right or on the left? On the right. But if you look at the intersections, there's no discontinuity, right? They're exactly the same color. It's again an example of where the background influences our perception of the foreground. Here, clearly there's a discontinuity, but if I separate those two, they actually look pretty much the same, right? So this is the inverse of that effect, that we can actually also make colors appear like if they are in fact not. And this is a figure from an actual paper that Bang Wong has like found for his points of view column. And so here, this is like a heat map as is used a lot in biology. And those two colors here, like where we have the stars, are in fact the same. But this here almost looks like it's a very low value at the top, right? Whereas this one here, just because of its environment, seems to be much darker. And so this is really tricky if we use heat maps like this. So there's these interaction effects that also happen a lot, and we should always be aware that color is always relative. Okay, so now I'd like to do a design critique. Can you guys help me hand this out?
Yeah.
Okay, so you'll get a sheet that shows you this visualization. This is a visualization that was cited by Bill Gates of his favorite chart of the year. It shows the loss of life over time also, or at least with change, according to various causes of death. And so please take a look at your handouts. And then there's some instructions. So this is what Bill Gates said about this chart. I love this graph because it shows that while the number of people dying from communicable diseases is still far too high, those numbers continue to come down. But there remains much to do to cut down the death in that yellow block even more dramatically. We have the solutions, but we need to keep up the support when they're being deployed. So take a look at your handouts. And there's some questions on there that I would like you to go through. You can, yeah. So there's a redesign part, and I actually brought scratch paper if you need more. So, and this is not I'm not going to grade this or anything. It's just an exercise.
Guys, how many of you? We need them all the way down here. I can out there.
Then can I actually have one? Or, okay. So please do this in read the stuff, but then find some neighbors and just have a discussion about it. And I'll give you 5 minutes. And then you should also think about a redesign. Sketch something. How could you display this data better?
You know, why didn't you go to
He wrote the discussion.
I like
right, so first, we want to ask the question is like, what is the data that is shown in this visualization? So, what data do you see here?
2010.
2010? Yes, but like, what is the data? Not just one point on the scale.
So, like, maybe I'm inferring this, but it's like the relative, like, categories. There's like three main categories, and it's like the relative number of deaths.
Yes, so we have the first thing that you correctly identified is there's three categories of cause of death, and what are they? Injuries, communicable diseases or infectious diseases and non-communicable diseases, right? So infectious diseases are things like malaria or HIV. Non-communicable diseases are things like heart disease, diabetes, or cancer. Okay, so these are the three categories that we have identified here. So that's one data point. How are those three categories encoded? By color, yeah. So we have three different colors, the green, the yellow, and the pinkish red. Okay, what other data is in there?
Relative change.
The relative change of how frequent the cause of death this was between 2005 and 2010. How is that encoded?
Using shades.
Exactly, color shades. So that's actually, initially this doesn't look like such a bad idea. Why? What could be my complaint about this color scale?
One that it's not good for colorblind people.
That is true. It's there. We have red and green.
So I think that for injuries and non-communicable diseases, we are basically altering the intensity. But the first one, we are switching between two colors.
Yes.
That is kind of inconsistency.
Yeah. So why do you think they did that? Because probably yellow would be almost white if they did the same thing to it, right? So they probably did that for that reason. What other thing do? Yeah.
Zeros are an arbitrary color.
Exactly. So it's really hard to spot what are the blocks here that didn't change at all, right? It's and especially like a slight increase versus a slight decrease is really hard to tease apart. So a diverging color scale here would have been better. And what's the third data type that's encoded here?
Proportion.
Proportion, yeah. And what does proportion encode? The number of cases, like the sum of, or the life years lost for one of these different diseases, or let's say causes, well, because road accidents clearly are not a disease. Okay, so what else is, there's another highlight, or a couple of highlights in here, a couple of call-outs, right? And so we have the cancer call-out, and then we have some annotations. Okay, so what question does this visualization answer? Yeah.
Way to focus the efforts to save more life.
Yeah. So that's good interpretation. Somebody else? Yeah.
Evolution of the diseases.
Exactly. Which are becoming more prevalent, which are becoming less prevalent. So what we see here is like this is if there's a call out. Natural disasters have increased a lot between 2005 and 2010, or is it 2005 and 2010? Yeah. It also gives us an idea of what it is that people typically die of. So, for example, this here, what is the biggest block here?
Heart disease.
Heart disease, yeah, but I mean the three categories, like infectious diseases looks pretty big, right?
Yeah.
And those are usually preventable. And I guess the message here is this is obviously a chart for the whole world. In like a completely industrialized country, I'm sure this would look quite a bit different, right? So you would have a much bigger block for the non-communicable diseases. So what else is striking about this chart?
Because the yellow and the green blocks share the same width, it's difficult to infer if yellow is actually what the relative size is to the pink block.
Yeah, that is really true, and that's a problem of the choice of these like nested squares that they've chosen here, right? What else is interesting about this chart?
The chart is visually appealing, and so if this goes up on a website, I would imagine you're more likely to garner support and funding for your pet project.
Yeah. So what makes it visually appealing?
It's nice, I can look at it and read 3 words and then feel like I felt good and all that.
Yeah, so one word I haven't heard yet that I'm trying to get at.
3D?
Yes, thank you. Why is it 3D? And I think the reason why it's 3D is because it's supposed to be catchy, right? It wants to, like, if you look at websites, something like this will draw your attention. If it's just a bar chart, it might not be quite as catchy. But what is the problem with 3D? Here. Yeah.
It distorts the proportions.
Exactly. So exact judgments are really hard to do here. We also have shadow here, and we know what shadow does to color, right? From what I showed you in the lecture. So it's really like 3D and color coding is really something that you should be very, very cautious about. And what about the labeling? Yeah, so we have these.
Yeah, some of the smaller squares don't even have labels.
Yes, that's a common problem for these kinds of maps. These are called tree maps. But also they're distorted because of the 3D, right? So if we had a 2D chart, we could at least like have absolutely readable text. And I guess the problem that the 3D solves here is like infectious diseases, injuries, and non-communicable diseases. There's of course much better ways to just label these. So how did you redesign this? Anybody want to describe the redesign?
A color-coded pie chart.
A color-coded pie chart.
It's also sorted in order.
How many slices does your pie chart have?
You can say others or something.
I did 3 blocked line charts, one for infectious diseases, one for non-communicable, one for injury.
Okay.
That the x-axis goes over time and the y-axis is the difference.
Okay, so you only have 2 data points here, right? You have 2005 and 2010, so you would have a slope chart because you don't usually have those between them, but that would be a good visual encoding, yeah? Anybody else?
We had a bar chart where things can go above and below the x-axis.
Yeah.
To better show the change.
Yeah. So what you did is explicitly encode change as a separate bar chart, which is a great idea because that's a trick that we as visualization designers have to make quite often. That we, instead of plotting the absolute data or the raw data, that we make some transformation. For example, we plot change instead of the absolute data.
3 triangles side by side, with the tiers of the triangle representing the portion that's growing and decreasing, and then you can separate it based on the 3 categories up there.
I would have to think about that. But it sounds like a creative solution. Okay, so there is a professional redesign. There's a guy, Stephen Few, who runs a blog, and he's like a consultant for businesses. And he runs a blog which is quite, let's say, popular. He's also a very, very opinionated guy who will get into a fight with you very easily on the internet. So I don't like his personality. I do like some of his work. So this is what he did with this chart. And so one thing that you will notice is this is not a chart anymore that is great to show on a slide, right? That's something that you would put in a book, and it looks like something that you would put in a government report. It's accurate, it's made for decision makers, it's not made to draw your attention. It's not made to compete for whatever you're doing on Twitter. This is really, if you are interested, then you should look at this chart because it is a better design for accurately reading the data. So first here, he separates it into 3 areas here. So he does years of life lost per 100,000 in bar chart, and we can see here, cancer is by far the biggest. So that was something that was visible in the other chart, but it wasn't quite as evident. And then we see heart disease is the second one. He color codes as they did before in 3 different colors for these categories: non-communicable injuries and communicable diseases. And then he plots, in addition to that, the change in the years of life lost, similar to what you guys here suggested. And so we can see that basically cancer didn't move. which is surprising if you think about how much research dollars are invested in the cancer, right? But this is also in the pre-genomic area, so I think that this chart would look a little bit different, and this is also for the whole world, and not for an industrialized country. And then you see that there is like a there's quite a significant downturn for many infectious diseases, which are gray. So you can see that respiratory infections, meningitis, hepatitis, HIV, and so on, all of those like have changed up to 30% are reduced. And then I think the other thing that he does is separate out death per 100,000 and life years lost. And this is not in the original chart. But if you think about it, it's quite an important consideration, because there's a difference if like a child dies in the Civil War or a 92-year-old person dies of prostate cancer, and like how dramatic we perceive an impact like this. And so life years lost is usually a better measure. So there's other detail, and there's a blog post, there's a link to the blog post on this slide. When I put the slide online, you can read more about it. I think this is a well-done chart, but it is also clearly not as catchy. And so maybe it wouldn't serve the purpose of the author as well as the original did. Maybe Bill Gates would not have picked this as his favorite chart of the year. Does anybody want to comment? Yeah.
I'll just say this one loses a ton of information though. Like cancer's all grouped into one thing, whereas the Bill Gates one has like lung, liver, breast, leukemia throughout.
So yeah, this one categorical aggregation here is lost, but you could still break that up, right, if you wanted to.
Yeah, I don't know if it's better or worse, but
it would make the graph, like you would have to actually scroll probably. So it's an interactive chart where that could be solved. But yeah, this is right. There's a lot more detail. It comes at a cost. So here there was a conscious choice to aggregate something. So what you could do, for example, is to make this an interactive visualization where you then click on cancer and then you break it out, right? What are the types of cancer? That would be a cool project. Okay. Any other comments before we talk about? Yeah.
I just thought it was interesting when you're looking across years lost, which is like death. I couldn't really tell what the three blue ones were. I couldn't read. But it's like it's interesting that like those are so high for like years lost, but that like absolute number of deaths for like 1,000 are actually pretty low. So it's like kind of giving you some information there.
I think that there's years of life lost per 100,000 and then death per 100,000. So
like there's a lower number of deaths for like that that first blue one underneath. There's like a lower number of deaths.
Accidents.
Not high.
So
sorry, is that
diseases.
is it the infectious disease if you go up?
the black one here, yeah.
Is that black?
Yeah, or gray.
So like there's like a small number of deaths for that, but it accounts for like a high number of years lost.
Yeah, neonatal or maternal disorders will usually affect young women and babies, right?
Yeah, I can't.
So yes, you cannot see that, but it's neonatal disorders, right? And so that's why that usually doesn't affect seniors.
Yeah.
And hence, it's not surprising that this is much higher ranked on the years life lost compared to the number of deaths, right? Like a baby that dies in childbirth, it's like 85 years of years life lost compared to somebody at 75 dying of cancer. So, okay, so one comment about the structure of the lectures, what happens a lot is that I don't finish my slides. And so what I'll do is I'll just keep going with that topic the next time we see each other. I will not do that on Tuesday though, because on Tuesday I need to teach about SVG, and so I have like probably 60 more slides and I won't get to them. And then I will continue the stuff on Thursday before I move to the next theory lecture. So Tuesday will be coding, Thursday I'll continue whatever I can't finish today. Okay, so the next thing that I wanted to talk about is pop-out. So pop-out are properties that are detected by the low-level visual system, and this is a very, very rapid thing. So if I use a pop-out effect, and some people call it pre-attentive processing, which is a term which has been fallen a bit into disfavor, we can recognize those pop-out effects very quickly, very accurately, and they're processed essentially in parallel. So the interesting thing is pop-out works if I show you 2 items or 500 items. The number of distractors doesn't matter. And the opposite of pop-out is sequential search. So this sounds very abstract. Here's an image that explains it very quickly. So like here, what is not like the others? There's a red dot. How long did it take you to see that? Immediately, right? And if I showed the whole slide would be full of blue dots, you would still have seen the red dot just as quickly. And so you can clearly tell there's a red dot here, there's not a red dot here. There's a red circle. So this works also for shape. Was it quite as fast? No. Okay, so there's a difference, right? It works, but it's not quite as fast. Also quick to spot, right? Orientation. It looks different, so we are quick to spot it. So actually what I wanted to do here is, I'll show you this and you clap as soon as you see the wrong element, okay? So let's do a test run. So what's going on here? Red circle, yes. And so red by itself has pop out, circle by itself has pop out, red circle in a sea of blue and red squares does not. So combinations of these pop out features does not work. So here you would have to basically go through everything and look at them individually or in small groups and judge, is this different from the other? So this is not a pop out effect. So it's not valid for combinations. There is like others. We had orientation, we had length, we had closure, we had size. There's curvature, density. So here we see a cluster. Then hue, obviously, the color value or the brightness. Up there we have one of those dots. And then this animation isn't perfect, you also see blinking pretty attentively, and then of course direction of motion. And these are very strong too, like flicker, you ignore the white, ignore those two pictures, this is just an artifact of the GIF, but if those are blinking or these movements, these are also very strong pre-attentive properties that we are easily able to recognize. Should you therefore make your visualizations bounce? Probably not, right? There's other reasons. This is very distracting, right? This draws your attention very strongly. You have a hard time ignoring it. So, what are the kinds of tasks that you can do with these pre-attentive or with these pop-out effects? You can do target detection, detect the presence or the absence of a target. You can do boundary detection, detect the texture boundary between two groups of elements. You can do region tracking. You can also have a reasonable sense of counting, like estimating how many items are different from the other very quickly. So here, for example, you don't know the exact number if you look at this number estimation example, but you know it's somewhere between 8 and 15, right? Just by looking at it. And boundary detection here, easy for hue. Again, for combinations, it's quite difficult to do. So as you all realized, the red circle in the sea of red squares is harder to detect than a red circle in a sea of blue circles. So there's a hierarchy of pre-attentive features. So hue is better than shape, for example. And so there's more examples online if you click on these images here. There's a couple of theories of how pre-attentive processing works. It's not a solved problem. I also don't want to make this into a psychology lecture here, so I would just refer you to this website that discusses all of these different theories. So why am I talking about this in a visualization class? Well, the thing is we can use these pre-attentive properties or these pop-out properties to draw attention to areas of interest. So for example, if you want to highlight an item in your visualization, it can also be used to express similarity or group membership. But the thing is though that the visual features, they must be carefully designed. So if you want to leverage pop-out effect to highlight something important, you cannot, for example, if you want to use hue for that, you cannot have a very colorful visualization. you have to stick to grayscale and use other channels to encode the data, and then you can use hue as an augmentation to draw people's attention. So examples here are cues for focus and context techniques. Do I have anything else? And obviously, conjunction must be avoided. So another really fun psychological effect is change blindness. So change blindness is about when we see something and cannot remember it across separate scenes, except when we really pay very focused attention to like a very small object on the screen. And an interruption, for example, if I show you an image and switch out that image with a blank screen and then show another image, you will have a hard time actually spotting any changes. And these interruptions, they amplify this effect. And this is not really a failure of a vision system, it's really a failure of appropriate attention guidance. And so here is an image. And there's something going on here. And raise your hands if you see something changing between the two images. So by now most people here have found it. We can actually, yeah. So you can actually see the shadow of the helicopter has been removed in one of the images. So that's a little subtle. Let's do something else. Raise your hand again if you see something change between the images. 1 person, 5 or 10. Clearly it takes you like a while to look at different regions of the image, right, to identify what is going on. You don't see it automatically. So what is? So here you can see that effect quite obviously. And then one more. Raise your hands again if you see it. It's pretty important for people to see. Yeah. Depicted in the image. So. The engine is missing, right? Again, various theories about the causes. Other things are like, when I tell you, hey, something is changing, this is like you're at the most alert ever, right? So you pay a lot of attention. But if this is just casual, and I'm using a visualization system, and something changes subtly, then somebody will not notice even more pronounced effects. Also, like attention, expectation, the semantic importance of an object. So for example, if I showed you an image, there's one person, and that person disappears, you will notice it, right? But it has to be something that a little bit in the background that you will actually miss it. And low-level object properties such as color are overlooked more easily. So here is another example. This is a gradual change. Did anyone notice it? There's a couple of people who noticed it. I'll play it again. I need to have a blank screen in between. But pay attention to the region here. Like there's basically somebody has mowed down the corn. Here is another similar image. Who saw something? Okay. Playing it again. And in this case, I knew what what I was looking for, but I forgot which stone it was, and I couldn't spot it the first time. So this stone down there. And then here is like a lovely scene from the 80s. Anybody notice a change?
I see it.
Look at the, well, I'll let you. So this person's sweater color. It's changed from blue to red. A similar effect is called attention blindness, but I think we'll talk about that next Thursday. So I'll see you guys on Tuesday. Please remember to fill out the homework survey for homework 0 if you haven't done so already. And then Tuesday we'll talk about SVG and So we actually only need to